In this video, I will go over the homework that follows the lecture, focusing on the topic of creating power series, which goes hand to hand with being able to recognize a function in a power series. And it's a two-way road. So on one hand, we know that a function can be expressed as a power series. On the other hand, we know that some power series converge to some functions. So as always, I hope that you watched the lecture, and let's go ahead and jump right into this homework. And the first question is this: given this series, the question is what is the interval of convergence? And we will figure out the interval of convergence, but here I want to actually do another exercise. We can actually play with this series just a little bit and write it like this. And then we can recognize this pattern and conclude that this series is actually equal to this function. Oops, without the series symbol, right? So it's just a function. So this is the function that this power series converges to, but it doesn't converge to it everywhere. It only converges on this interval. So to obtain the interval of convergence, we have to solve this inequality. So x cubed will be less than 1, or rather 27x cubed will be less than 1 or negative 1. So x cubed will be between 1 over 27 and negative 1 over 27. And then x will be between 1/3 and negative 1/3. Now, this is our interval of convergence. We don't have to verify the endpoints because this interval was obtained analytically and not by using the ratio test. So this is our answer. Now, this is interesting because I was just staring at it. Because it's not a power series the way we know it, because we now allow x to have negative powers. However, the ratio test doesn't care about that. And if we set up the ratio test, so we take the n plus 1th term and divide by the nth term, and then we simplify. So we're going to end up with pretty much everything canceling, and we're only going to have x minus 3 to the power 7n plus 7, so it's going to be, looks like negative 7. And since it doesn't depend on n, we can literally just remove the limit symbol. And now this has to be strictly less than 1. So when 1 over x minus 3 to the power 7 is less than 1, that means x minus 3 to the power 7 has to be greater than 1. That means x minus 3 to the power 7 is greater than 1, or I guess we're now getting rid of the absolute values. So x minus 3 is greater than 1, or x minus 3 is less than negative 1. So x must be greater than 4, or x must be less than 2. And now we need to figure out what happens at the boundaries. So we're going to set x to be 4. And if you set x to be 4, then you end up with the following series. You just have a bunch of 1s. And this series diverges. And when you set x to be 2, you're going to end up with negative 1 to the power 7n minus 9, which also diverges. So we don't include the boundary points. So now in the interval notation, the interval of convergence will be expressed like this. So again, even though it looks odd, it does make sense somewhat. Right, so this solution is a little unintuitive, so I would stick to the ratio test. All right, moving on. We have a function 6x squared divided by 1 plus x to the 9. We've seen problems like this before, so let's just transform this into a series. And we're going to have 6x squared times series, and goes from 0 to infinity, negative x to the 9 to the power n. We're going to do two things here. We're going to bring the 6x squared inside, and we're also going to distribute the power n over. And now we're going to combine everything and simplify. So we have negative 1 to the power n times 6x to the power 9n plus 2. Even though it's not asking for it, I'm going to recognize this pattern and write the function to which this series converges on this interval. To find this interval, we have to solve this inequality. We divide both sides by 343. And cube root of 343 is 7. So since we did it analytically, we don't have to verify the endpoints. This inequality is the interval of convergence, and we're just going to write it like this. And it looks like we have completed this homework. And if you have any questions, please reach out.